So let's look at two parallel wires with current flowing through them. So here's a current carrying wire. Use the first, hello, there's nothing up there. Use the first right-hand rule and draw the magnetic field created around that wire. So current is traveling up. Draw the magnetic field around it in like a three-dimensional view so that you can tell which way the magnetic field is pointing. So using your right hand, figure out which way the magnetic field wraps around that wire. We're not doing this. It's not the physics gangster symbol, not yet. Doing just this one. Does my picture make sense to you? Okay. So that's the magnetic field surrounding the wire. Okay. On this side of the wire, which way does the tangent spot to the magnetic field point? Up, down, left, right, in, or out? Out, correct. On this side, which way? In. Very good. All right. Now let's take another wire and put it fairly close by. Okay. It also, so I'll call this I1 and I2. It also has an accompanying magnetic field. Same direction, so everything's all the same. Okay. So now I have two magnetic fields, B1, B2. The reason that we use current carrying wire and magnets together in generators and in motors is because they push on one another. And if you can see from this, if you have two wires that have magnetic fields wrapped around them, those magnetic fields will push or pull on each other, right? So how do you tell the direction that these fields push or pull on each other? In other words, will the wires be pulled together, pushed apart, or have little to no effect? Let's find out. If I now use my second right-hand rule, my physics gangsta symbol, and I have, let's say, these magnetic fields, which you said are going into the board, right? Okay. And so I want you to imagine that this is like a permanent magnetic field, and we bring wire 2 up close to it. Using the second right-hand rule, physics gangsta symbol, use your right hand with this wire to try to figure out the impact of these X's, these tails of the magnetic arrows, on this wire. So your index finger should point up. Which way should your middle finger point? Toward the back of David's head, right? Into the board. Which way will your thumb be pushing now? Yes. So that means, to the left, that means that wire 2 is actually pulled toward wire 1. That's F. Also, remember that you guys said that on this side, because these are identical, on this side, the magnetic field is pointing which way? Out. So just based on what you know about magnets and what do you think happens when you have magnetic field lines pointing in opposite directions? They attract. That's correct. It's like putting opposite poles together. This actually has some real-world applications, and that is that if these wires get too close together, they can actually overheat and start a fire. And so when you design circuits, you don't want the wires carrying current in the same direction that are close to one another. So what would happen if instead of I2, the current traveling in the same direction as I1, what if it went in the opposite direction? What do you think the effect would be then of these two interacting wires? Instead of attracting, what would they do? They would repel. So you actually do have to be cautious because of those interacting magnetic fields as to how closely you put wires, and you could use the math here and figure out how strong is that attractive force, and will it actually pull those wires close enough so that they could overheat, cause a fire. All right, let's look at another application. Say we have a strong permanent magnetic field. We actually used an example like this. Oh, actually, I want to do it differently. Slightly differently. Yes?
Could I stick these in there for
Sure.
to give you some?
All right, let's do it this way instead. So you don't have to visualize the in-out part. Okay, so instead, here I have a magnetic field pointing into the page, into the board, okay? And I'm going to take a little positive test charge and fling it into the magnetic field. Okay, so that's Q. That's also the same as I, because current is positive charges. So I want you to use your physics gangsta symbol and tell me which way that charge will be pushed. Josh is correct, it's up. We actually did this yesterday. So it'll be pushed up, right? You guys are correct. So like this, it gets pushed up. Then once it turns and it's moving up, which way does it get pushed? To the left. And then once it turns to the left, which way does it get pushed? Down. And what shape will that make? A circle. And what's the application for, what's the place where they shoot charged particles in a really big circle? The one in Lucerne, Switzerland, yes. It's the super collider, the Large Hadron Super Collider in Switzerland. Well, what kind of forces are these when you have charged particles moving in a circle? Centripetal forces. So we can actually combine flying charges moving in a magnetic field with centripetal forces. Who remembers what the equation is for centripetal force? There's a radius in there. Does that look familiar? Yeah. So, this is another very commonly used application in particle physics. The relationship between a moving charge in a strong magnetic field is equal to the mass of that charged particle, how fast it's going, and inversely related to the circle radius that it makes. Okay. So you may see this application. All right. There's one other new thing that we need, well, very difficult new thing that we need to learn. And I think I'm just going to talk for a couple of minutes about it conceptually. What I'd like you to do in terms of 21A and B is I will put up all the answers. If you want to do some more practice, you practiced a couple today. It looks like everybody was successful. That would be great. I will quiz you on the ILB, QVB stuff tomorrow. Ready? So if you want more practice tonight, do that to prepare. If you're like, ooh, I rocked with this stuff, don't worry about it. All right? So let's talk conceptually.